Hey class, welcome back to class. This is our first online session. This is Mr. Roberts at Shasta High School. Today we're looking at section 8.2.2. This lesson is going to be one where you're not required to fill a lot out in the notebook. In fact, I don't want you to fill anything out in the notebook. Feel free to write. You can draw, type in it if you wish, but not required. There is going to be a participation quiz at the end, and some of the things we discussed today I'll just ask you to echo back and see if you've got those. So you might want to jot down a couple of notes as we go. You can always rewind the video and find answers as well. So far we've looked at a variety of linear models, but what happens when the best model is not linear? And they take us all the way back to the dry ice problem. I think this was in chapter 5. Julia's father uses dry ice to keep the glasses in his restaurant very cold. Dry ice does evaporate in a restaurant cooler as shown in the table at right. So we're asked to create a scatter plot and to find the least square regression line of this data on our calculator. I suggest doing this with Desmos because we're here and we've got it. So I want to talk about kind of how that happens. Desmos in the book, the links that are always there pretty much take care of everything, and you don't have to think about or do anything. And I just want to see what it looks like for us to actually do this. I did import the data, though, separately, so we don't have to type it in. So let's go ahead and see if we can recreate the linear model using the link to Desmos. So when I follow the link, I get this data set that's typed into the left and the scatter plot off to the right here. The scatter plot, at first glance does appear to be linear. And if I was to find the line of best fit, I'm going to go ahead and add an expression. To get lines of best fit that are linear, basically we type, if you look at this, my x's are stored in x1 and the y's are stored in y1. So what I type is just y and then the number 1. It automatically makes it a subscript like that. So you just type y1. Don't worry about getting it into the subscript. And then if you hit shift and tilde, it's this character. It's on your keyboard, it's below escape or above the tab key. So y1 tilde, and then I'm going to say mx1 plus b. So mx1 and then plus b. Let's see. Plus b. And when I do that, you can see that I have this line that does a pretty nice job of fitting the data, especially if I zoom in a lot. It looks like the data is very close to the line. You can see I've got R, my correlation coefficient is negative 0.9979. I'm just reading it from the screen. The coefficient of determination there is 0.9958. So I would say it's a very strong negative correlation. As the number of hours past noon increases, the weight of the dry ice in ounces decreases. And I just remind you that we talked about whenever we look at a residual plot, if we see a pattern in the residual plot, it's an indication that a linear model is probably not best. And you can almost see this. It's kind of you can see a slight curve in the green dots, but when you go ahead and plot the residuals, and I'm going to scroll down here so we can see the residual plot. And the other thing I'm going to do is I'm going to elongate the x-axis so that you can get to where we can see more and more of it. And you can see there's this very clear pattern, right, in the residual plot where I start high. The residuals are all above 0. And then somewhere around hour 1, 2, 3 past noon, the residuals become negative, and they stay negative all the way until around here, 8 hours after noon, and then they become positive again. So when we see a pattern like that in a residual plot, we see a high, low, high. That's a good indication that a linear model is probably not the best model for our data. There's something perhaps going on. And if we want to look at this and see what the another potential model could be, we're going to go ahead and look at an exponential model. So I'm going to zoom out a little bit here. And actually, I think I'm going to go ahead and ask it to turn off the residual plot. And we're just going to look at our data again. But this time, instead of looking at a linear model, we're going to look at an exponential model. And you've guessed it, maybe you've guessed it. We're going to say y1, and then I'm going to hit shift tilde. But instead of doing mx1 plus b, we're going to go a times b raised to the power of x1. So we're asking it to come up with an exponential model. And when I press enter, you can see it's got a new curve that it's giving me. And if you scroll out more, you can see that the behavior past those hours looks very different. It makes sense that you're never going to have dry ice, negative dry ice. So I like this model because it does show that this becomes an asymptote with the x-axis, and meaning it just approaches it more and more. Of course, the dry ice is going to be gone. The CO2 will evaporate, but this model does a much better job of fitting it. The other thing we can do is we can look at the residuals of this exponential model, and there's not much of a pattern in the residual plot, meaning, I mean, it's a good indication that it's probably a better model. There is not a correlation coefficient, but there is a coefficient of determination, and you can see it's slightly higher. So anyways, this is one possibility when you're looking at your data. You can see that a line may or may not fit it. You can look at perhaps an exponential model, and there's other models we'll consider as well. Let's go back to our page. So what type of function might fit this data better? Probably an exponential model. It does ask, what does the residual plot tell you about the data Julia collected? That residual plot, because it went high, low, high, indicates that a linear model is probably not the best. Use your calculator to determine the exponential regression equation. Add this graph to the scatter plot sketch rather. Be sure to label the graph with the equation. So you can see that there again, the equation we came up with, you can see there's a value of a and b. We've got y equals 15.4, if you're going to round to the nearest tenth, 15.4 times 0.96 raised to the x power. So that's that curve that we see in green, rounded to the nearest tenth. It does ask us below, it says make a, based on the scatter plot alone, does the linear model or the exponential model appear to be a better fit? Well, they both really fit kind of nicely if you're just looking at the scatter plot. It does say make a residual plot of the exponential regression and comment on the appropriateness of the exponential model. So let's go ahead and turn that on. We didn't actually look at that, so I'm going to turn on the, I hope I can turn that on. I think I can turn that on. I'm going to plot the residuals for that. Oh, that's interesting. There, I mean, I didn't zoom in at all, but you can see those are, I wonder if I should turn on the other one. Well, it's interesting because I tend to see, I think I see some kind of a model there, but the black dots seem to be a bit more scattered, right? They're they're below, above, below. Whereas the green residual plots from our linear model seem to be high, low, high. The black ones seem to be scattered around a bit more. So based on the residual plot, I think I'm happier with the exponential model as opposed to the linear model. All right, let's move on to the next question. Below is a list of amounts of oil produced from 1905 to 1972. MMBBL stands for millions of barrels and is the standard abbreviation used in the oil industry. So you can see we start at 1905 and we go all the way up to 1972. And it says create a scatter plot of the data on your calculator and sketch the results on your paper. And then this is an interesting thing. It says treat the year 1900 as year 0. So if 1900 is year 0, that means when x is 1, we're looking at 1901, right? When x is 0, we're looking at 1900. The first year that we have data is 1905, where it's 215 millions of barrels. So let's go ahead and take a look at our scatter plot. So we can see it, and the data is here, and just based on the shape of the scatter plot alone, I know that a linear model is not going to be appropriate. The residuals are going to be fairly off and not adequately predict what's happening here. So let's go ahead and build the exponential model for this data. Same thing we did before. I'm just going to add something to the graph. So I'm going to hit add an expression. And we're going to add, we're connecting y1 and y2. I'm pretty sure these were y1 and y2. Let me look again. Yeah, y1 and x1. So we're going to say that our y values, y1, are equal to a times b raised to the x1 power, and press enter, and I have an error. The reason why I have an error is I use the equal symbol and not the tilde. So I'm going to go ahead and hit shift tilde, and you can see it's come up with an exponential model. Now I do see that early on the model seems to be under predicting the amount of oil that was produced. The green dots are above it, but about by the time this is like 1940, 1945, it looks like it's the thickness of the dots are definitely on the model. And I could ask it to plot the residuals. The residuals are kind of high, low, high, low, high. They're fairly all over the place. Let's go back and see what the book's asking us to do. It says, does it appear that a linear model will? No. A linear model will clearly not fit that data, and I didn't even ask it to graph that. So no. It says what model might fit the data better? Well, an exponential model, as far as we know, it looks great, and it's definitely a tool that we have. It says now use your calculator to determine the exponential regression equation. Add this curve to the scatter plot sketch. Be sure to write the equation near the graph. So as we move forward, if I ask you to do things like that, it's certainly fine with me if you just screenshot your Desmos. Just go ahead and on any device you have, just kind of capture the screen, and you can place that in the notebook. And that's going to be different for every device. So I'm not expecting you to get out graph paper and take a picture of graph paper and send it to me. I'm very happy to see that you can use a tool like Desmos or GeoGebra, and you can figure out the regression model just by typing this in. And again, you can see it's y1 and then the tilde ab to the x. So this equation, if I was going to write it, I would write something like, oh, as soon as I start writing, this is going to disappear. Let me see, I can put it down here, and no, I'm not going to be able to see that. But it's y1 is equal to a, which is 110.13. I probably go 2 decimal places. 110.13 times b, which is 1.07 raised to the x power. And that's this curve. And basically it's nice because now it gives us a way of putting in data that we don't know and asking, well, in the year 1986, in the year 1985, or in the year 2000, how many millions of barrels of oil would be produced if this trend persisted? It does say make a residual plot of the exponential regression, comment on the appropriateness of the exponential model. If I look at that again, I do see that it's high, it's low, it's high, it's low, it's high, it's low. It's not one pattern where it's just high, low, high. I can see that it's the points are roughly above and below at different points in the graph. So definitely a better model, and if we were to look at the residual plot of the linear model, it's definitely better than that. Okay, we are going to just briefly talk about this piecewise model. The idea here is that sometimes when you come up with a nice model, the model makes good predictions for a while, and then the predictions are not so good. And if I was to look at this data, to give you an idea here, so this is our original data, and you can see something happened, and basically the production was going, and then all of a sudden it kind of plummeted around the year 1980. And I don't know if it's because all of a sudden there were more efficient cars on the road. I don't know exactly the speculation. I do know that in my lifetime, that was around the time when we had, kind of an oil crisis, some oil embargoes, and I think that's around the time that OPEC was formed. So there was a shift downward in production. And the curve looks like it changed after that. It looks like after that, it doesn't have quite that steep exponential growth that it did, and it looks like it's somewhat more linear in nature. So maybe we got more efficient at using oil, or we found other energy resources. The point of this is that sometimes when we build a model, sticking with the same curve the entire time may not be appropriate, because, like, for example, here we can see behaviors change. So when we talk about a piecewise model, what we're talking about is sometimes we want to build a graph where for a while, right, a portion of our activity is behaving a certain way, and then at a certain point in our domain, so let's say that this is from 0 to 10, one thing's happening, and then from 10 on, all of a sudden it's not exponential. It's totally curved off. Or it could be at 10 on, maybe it's even decreasing. So what a piecewise model does is it says, first of all, there's different ranges. So it might say for x values that are greater than 0, but less than 10, we have one equation, y equals, and this looks exponential, right, ab to the x. And then maybe at a certain point past that, when x's are as soon as x's are greater than 10, we can say now we have a different behavior, right? Y equals, it could be linear at this point, mx plus b. So the idea here is that typically models that track these things are not, it's not the same for all portions of the domain. Part of the domain may need one thing, part of the domain may need something else. Okay, we're going to end our time today by talking about how you could perhaps find an exponential function that goes through two given points. So I've got the point 2, 144 and 6, 729, and the question is, thinking about a sketch of those points, right? I've got 2 is 144 and 6 is way up at 729. Can we come up with the curve in the form y equals ab to the x that would hit both of those points? It just has to hit both of them. Y equals ab to the x power. And we talked about this a little bit, and this is kind of where we were at before class was disrupted. So let's see if we can take a look at how to do that. So the technique that's discussed here, in fact, you can read through this. This is in the math notes section of your textbook, and your online textbook still works. So you can look at this, and this is a different example, but I'm going to work through this example with these two numbers. So I'm considering the fact that I want the equation to be in the form y equals ab to the x, and I've got two values of x, y, right? Here's one xy and another xy. And I'm going to use these two different values to write two different equations. So the first equation I'm going to write down is, you can see the top one there, y is 144. So I'm going to write 144 equals a times b to the second power. So I've just replaced y with 144 and x with the number 2. And the other equation I have is 729. Y is 729. And that's going to equal a times b to the 6th power. So I'm trying to figure out what my two parameters are. My parameters are a and b, and I've placed in two different sets of the variables x, y to discover what the parameters are. When we did this early on, it was very easy for us to figure out a because they typically gave us the y-intercept, but now you can see we're 2 away from that. Now, there's a lot of techniques. This is a purely algebraic technique, but you certainly could put the values in a table and to talk to yourself about how this is growing. But I want you to look at and become proficient with the algebraic technique as well. Sometimes the numbers aren't going to be quite as nice. So the technique we talked about was isolating the variable a in both equations. So I'm going to write these two equations again, and in both of them I'm going to get the variable a alone. In the top equation, if I want to get a alone, I'm going to divide both sides of that top equation by b squared. So it's going to become 144, oops, let me not write this in red, 144 divided by b squared is going to equal a. So again, all that is that top equation rewritten by dividing both sides by b squared. We're going to do the same thing with the second equation. We're going to divide both sides of that by b to the 6th power, and we're going to get, our numerator is going to be 729. On the left hand side, I'm dividing by b squared. I get this, or b to the 6th, so I get 729 over b to the 6th. And on the right hand side, when I divide both that by b to the 6th, I'm left with just a, because clearly a times b to the 6th over b to the 6th is a. What I have now is a situation where I could do, you can think about it as substitution, right? This, right, the top equation tells me that a is 144 times b to the 2nd power, or 144 divided by b to the 2nd power. I can replace a in this second equation, right, with this value of a from the top equation, right? You can also think of this as the equal values method. Since a is equal to itself, we can set these two expressions on the left-hand side equal to each other. I'm going to choose to think about it as rewriting it by doing this substitution for a. So I'm just going to write that second equation again. The second equation has 729 over b to the 6th power. But instead of writing a on the right-hand side, I'm going to write what the top equation informed me a is, which is 144 divided by b to the 2nd power. What's nice about this is a great candidate for fraction busters. I can get rid of the fractions just by multiplying both sides by b to the 6th. That would eliminate b in my factors of b in my denominator on both sides. So I'm going to do exactly that. I'm going to multiply both sides of this equation by b to the 6th power, right? B to the 6th power. And I am showing it as b to the 6th power over 1, just so I'm sure that I understand that there's a numerator and a denominator. And I'm going to write it out all the way right here, 729. Here's my times b to the 6th power, right? That's what this brought in. I pushed across a factor of b to the 6th in that numerator, and it's over b to the 6th power. Over here I've got 144 times b to the 6th power over b to the 2nd power. Now over on my right-hand side, or left-hand side rather, you can see I've got this giant one, b to the 6th over b to the 6th, which leaves me with just 729. And on the left-hand side, I've got b to the 6th power over b to the 2nd power, which is going to give me 4 factors of b. So this is going to be 144 times b to the 4th power. Okay, I'm going to isolate b to the 4th now by dividing both sides of this by 144. It's going to give me 729 over 144 equals b to the 4th power. And you'll notice I'm not really concerned with arithmetic at all. I'm just going to save that for the end. The next thing that I'm going to do is I'm going to eliminate this 4th power that b is being raised to by raising both sides of this to the 1/4 power. So this I'm going to raise to the 1/4 power, and this I'm also going to raise to the 1/4 power. B to the 4th power raised to the 1/4 power is going to give me just b on the left-hand side. And on the right-hand side, when I raise that to the 1/4 power, let me grab my calculator. You might want to experiment with different online calculators, or maybe with a graphing calculator on your phone, or even for expressions like this, you can evaluate these a lot of different ways. But I'm just going to go ahead and use this calculator. I'm going to go open parentheses. I've got 729 divided by 144. I'm going to close the parentheses. I'm going to raise that to the power of 1 divided by 4. Now, I know how this calculator works. This 1/4 power is up in the numerator, and I can clearly see that. You may have to use an additional set of parentheses on the calculator that you use. But when I do that, I end up getting that b is, oh, what a beautiful number. Did not expect that. B is just 1.5. So we can go ahead and write down the value of b is 1.5. And now there's just one more question we've got to ask. We have to ask, what exactly is a? We know that b is 1.5. If we had a, then we could write the equation. Well, it turns out if we go back up here, there were several ways to figure out what a is. 2 of them. And I'll just kind of highlight these with this big green box right here. These both are ways to figure out a, and I'm just going to quickly use both of them. On one of them, I'm just going to say, look, a should be 144 divided by that value b I found squared. When I do that, it tells me that a is 64. And I'm going to do it with the bottom equation too as a check. If I take 729 and I divide that by, I'm going to grab that b again, up, 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 up. There's b. And I'm just going to raise that. I'm going to square that. And when I do that, I get a different number, which is alarming to me because I didn't raise it to the 6th power, did I? I'm supposed to raise it to the 6th. So let me correct this equation. It says you are going to take 729 and divide it by b to the 6th power, not b squared. When I do that, I do get 64. So luckily that means that we know both a and b. We know that a is the number 64, b is the value 1.5, which is 3/2, but I'm happy with 1.5 also. So the equation that we're looking for is y is equal to 64 times 1.5 raised to the x power. So that's just a single example, and we'll probably come up with some more of those. But anyways, there's the participation quiz. Most of the questions are just going to be just repeating things that you saw in the video. One of the questions is probably going to ask you to attempt to do this technique to solve, to write the system of equations for an exponential curve that goes through 2 given points. We are exactly at 28 minutes, so I think that's more than enough time. Go ahead and answer the participation quiz, and I look forward to seeing you tomorrow.